Okay, welcome to our last section on thermochemistry. Well, this is the last of the C work and it covers phase changes. If you take a look at your unit organizer, you can see that we're going to be covering the last box on state changes. And state changes and phase changes essentially means the same thing. So in this section, you want to understand what are the three primary phases of matter. What are the terms associated when you change one state of matter to another? How do these changes of state affect the release or absorption of energy? And how do you calculate the heat of fusion or heat of vaporization? Now, states of matter, as I was saying, can also be called phases of matter. And we've got three primary phases that we deal with here on Earth. We've got the solid, we have the liquid, and we also have the gas phase. And if you take a look at the diagram here, you've got these little purple balls, and with the solid, they're very neat and orderly, and they're not moving around. On the liquid, in the liquid phase, they're not as orderly, and you can see there's some movement on them. And in the gas phase, you have the most disorder of them all, and they really move around a lot more. And so what happens is as you move from solid to liquid to gas, your kinetic energy increases. Okay, so solids have the least amount of kinetic energy and gases have the most amount of kinetic energy. And if you think about it, if you've got a solid sitting there like your pencil on the table, it pretty much just sits there, but the air in the room continually is moving around, and that's because it has a higher kinetic energy. Now, there's another way we can look at the different phases of matter, and this is a diagram illustrating those different phases using water. So you've got solid water, also known as ice, and then liquid water and water vapor, which can also be called steam. Okay, well, when solids go to liquids, it's considered to be melting. When your liquid water becomes a gas, you are vaporizing it, and you can do the changes in reverse too. When a gas becomes a liquid, you're condensing it, and when a liquid becomes a solid, you're freezing it. And these terms work for everything, not just ice. Okay, so if you think about a gold ring, it's in its solid form or it's been frozen at that point because it's not a liquid or a gas. Now you can jump straight from the solid phase to the gas phase. And we can do this, you've probably seen it with dry ice, where solid carbon dioxide can go straight to gaseous carbon dioxide. It goes straight through melting and vaporizing, and so we call this sublimation. Carbon dioxide, solid carbon dioxide, or dry ice sublimes. You can also take a gas and go straight to a solid. This is deposition. We see this primarily, an everyday example of this would be frost. Okay, at night the water vapor in the air will sometimes go straight into the solid form over the course of the evening when the temperature drops real low and the pressure's just right, and you get the water vapor in the air becoming frost on the ground and on the cars and everything. You can also see this in your freezer if you've accidentally left your freezer open, and you'll see around the mouth where the freezer was open little ice crystals. And those have formed because your freezer has taken the water vapor in the air and turned it straight into solid ice. Now, another way to depict these changes is on a heating curve. And a heating curve can look just like this, or it can also go in the reverse direction, stair-stepping down in the other direction. And so you can see I've got heating gases and liquids and solids. And the lowest point's always the solid and the highest point is the gas. What happens here on these flat parts is you have phase changes. So here on this red line at the liquid area, that's when my liquid is becoming a gas. And down here at this lower red line, this is another phase change where my solid is becoming a liquid. Okay, it's in the process of melting. And what happens, what you really need to know here is that there are no temperature changes during a phase change. If you look at temperature here on the y-axis, temperature, that's why the line's flat. There's no temperature going on. You're still putting energy in, but what's happening is the energy is being used to increase the kinetic energy to take that solid and melt it into the liquid, or to take that liquid and vaporize it into a gas. So the energy is not being used to raise the temperature. The energy is being used to change a solid to a liquid or a liquid to a gas. So there's no temperature changes when you're actually going through a phase change. There's more things we can learn here on a heating diagram or a heating curve. As you go up the heating curve, you're going from solid to liquid to gas. And when you go from solid to liquid to gas, these are endothermic changes. It's absorbing energy to make those changes. So to take a solid, like a piece of ice, and to melt it into a liquid, that's an endothermic change because you have to put energy in. Okay, endothermic, you have to put energy in to melt that ice. The same thing to take that water and make it water vapor or steam. You have to put energy in order for that to happen. Now, if you're traveling down a heating curve and you start from a gas and you move to a liquid or a solid, that's exothermic. You have to take heat out in order for that to happen. So if you think about going from a gas to a liquid where you're condensing something, you're decreasing the kinetic energy, and so you're having to remove that energy. It's being given off, and it's considered an exothermic process. Okay, these flat parts actually have another term associated with them. So it's not just phase changes at the time, but when you go from a solid to a liquid, that phase change, you need to use the heat of fusion. If you think of fusing something together, when you fuse it together, you're like gluing it together and making a solid. When you go from a liquid to a gas, or vice versa, when you go from the liquid to the gas, you're vaporizing something. You're making a vapor. So when you're trying to determine what numbers to use, you're going to use the heat of vaporization. Because what we're building to here is trying to figure out what energy it takes to change things from one state of matter to another. Last section, what we did with our Q equals mc delta T, okay, when we did that formula, those formulas correspond to these blue lines on the graph. Okay, so what we're going to be doing now is we're going to try and figure out how much energy it takes to make the red lines on the graph to change a solid to a liquid or a liquid to a gas. Now again, with your periodic table, you have the information given to you. The formulas are here on the back of the periodic table: latent heat of fusion and latent heat of vaporization. So essentially, they all have the formula of Q equals mass times the change in heat, either fusion, or Q equals mass times the change in heat, vaporization. Okay. Notice there's no temperature change at this point. If we were to do a delta T on this diagram, well, that flat part has no temperature change, so it would equal 0. So we have to use a slightly different calculation. They also give you the latent heat of fusion of water and the vaporization of water there, because the heat of fusion and the heat of vaporization, just like the specific heat, are constants that can be given to you to work out a formula. So let's take a look at a sample problem. Or not. Come up, sample problem. Okay. How much heat is absorbed when 24.8 grams of water at 100 degrees Celsius is converted to steam at 100 degrees Celsius? So we're going from water to steam. So this is heat of vaporization. So this is going to be Q equals mass times the heat of vaporization. And if you take a look at the back of your periodic table, okay, the heat of vaporization for water is equal to 2,260 joules per gram. So at this point now, it's really easy to fill in our numbers. Q equals the mass. Well, we're given 24.8 grams. And then our heat of vaporization of water, 2,260 joules per gram. You multiply those two numbers, okay, and you get 56,048 joules. Now, a lot of times you'll see these in kilojoules, and it's a real simple conversion. 1 kilojoule equal to 1,000 joules. Okay, so 1 kilojoule is equal to 1,000 joules. So if I want to change this into kilojoules, I have joules up top to start, so diagonal down has to be joules, and then up above it we're changing it into kilojoules. And if you look at my conversion, next to kilojoules there's a 1, and next to joules there's 1,000. So we divide. So when you divide that, that's going to get you 56.048 kilojoules, but we can only have 3 significant figures, so 56.0 kilojoules is our final answer. It would be okay to leave it in joules, but like I said, a lot of times at this point they're converting things into kilojoules because the numbers are bigger. So you want to be sure you know how to do a joules kilojoules conversion. So take a look at our next problem. How much heat is released when 15.0 grams of water at 0 degrees Celsius is converted to ice at 0 degrees Celsius? Again, notice you have no temperature change. That's your Q. You're going to be doing Q equals M times the heat of, well, now we're talking about ice, so this is going to be heat of fusion there. And the heat of fusion for ice given to us on the periodic table, or on the back of the periodic table, is 334 joules per gram. So Q equals the mass, 15.0 grams, and then the heat of fusion, 334 joules per gram. I get that set up there. Now, heat is being released. When heat is being released, that is an exothermic reaction, and that means my sign is going to be negative when I do this. On the previous problem, it's absorbed and you get a positive sign. So you can put it there like I did next to the 334, or you can just change the sign of your Q at the end. So 15.0 grams times 334 joules per gram gets me Q equals to a negative 5,010 joules. And again, if you want to change joules to kilojoules, 1 kilojoule is 1,000 joules. And we can have 3 significant figures because of that 15.0. And for my answer, I'm going to have a negative 5.01 kilojoules. Okay, so negative 5.01 kilojoules, or as I said before, you could have just said negative 5,010 joules. Either one would be for an answer. So very simple problems, considering you have to be given the heat of fusion in order to calculate them. And as you can see on your periodic table, you're given those values. A lot will be written in the problem, but you want to know that they're available to you on the back of your periodic table. So when you're taking a quiz or a test, that's where you want to look for the information. So at this point, you want to take out your unit organizer and go ahead and fill in the information you've learned about state changes and heats of fusion and heats of vaporization.